Okay, welcome to your Wednesday. I think I'm doing this on, I don't know when it's gonna post. Welcome to your Wednesday Math Minute, the only Math Minute guaranteed to be on Wednesday and guaranteed to be no more than 10 minutes long, although this one's gonna have to be short because I have to go. I want to talk about identities and inverses. So I've been thinking for a few days about how to identify an identity. No, that's not right. How to define an identity. And what I started with was any mathematical statement that is self-evidently true. But as I've thought about that, that's really not quite right, because when you get to trigonometry in a few years, you're going to be looking at a statement like cosine squared theta plus sine squared theta equals 1. And while this is definitely true, it's not the kind of thing I would call self-evidently true. So I don't think it's quite right to say we want a mathematical statement that is self-evidently true. Instead, we want a mathematical statement that we take to be true on its own and that illustrates a relationship. What do I mean by that? Well, the identities I want to look at today are the additive identity and the multiplicative identity. So the additive identity is this idea that if I'm working with addition, so no, not identity. If I'm working with addition, what would be nice is to have some element that actually I could add things to, but it wouldn't change anything. And what is that element? What can you add to something that does not actually change the something? I'm sure you're yelling out at home, 0, right? So in general, we could say a plus 0 is a. This is the additive identity. It confirms the relationship for us that it's possible to perform something under addition using an element that does not actually change the value that you start with. So that element we're going to call the additive identity element. And again, for addition, it's 0, right? If we want to do the same thing for multiplication, if we want a multiplicative identity, then we need something, let's call it m, such that under multiplication, it actually leaves m alone. It doesn't change anything. What value is that? Again, I'm sure you're screaming uncontrollably at home, 1, right? M times 1 equals m. And so we can also, under multiplication, use the operation multiply by something such that it actually leaves the original thing we started with alone. And so we would call that element 1 the multiplicative identity element. So why does this matter? Well, in the first place, because again, we end up in lots of scenarios where it's useful when we're solving algebraic equations to use zeros and ones. It lets us solve things we couldn't otherwise solve. So if you want an example, e.g. for addition, let's say you have something like n plus 5 equals 12, and you want to solve for n. One way to solve that is to try to make a 0, to try to utilize the additive identity. If I can add negative 5 to both sides of this equation, I can get that n on its own, because 5 and negative 5 make 0, 12 and negative 5 make 7, and now the additive identity tells me n plus 0 is the same thing as n, and so now I have a solution, right? When n is 7, that equation is true. Or if I want to do the same thing for multiplication, let's say that I have something like 3 times n equals, let's go again with 12. Now I know that I want to make a 1, because under multiplication, I need to multiply something by 1 to know that actually it's just the same as whatever I started with. So in this case, to get rid of that 3, which really means to turn it into a 1, we're going to multiply by 1/3. You'll notice in all of these scenarios, anything that I'm doing on one side of the equal sign, I'm doing on the other. There is a reason for that we'll talk about later on, but not today. And so there it is. When I multiply by that 1/3, I get 1 times n equals 1/3 of 12 is 4. And again, the multiplicative identity this time tells me 1 times n is the same thing as n, and once again I end up with a solution. Now, I told you at the beginning that I would connect identities to inverses. So again, I think this is pretty cool. Let's say we want a reason to do what we were just doing on the previous page with those equations. Why was it that I knew 5 and -5 would get me that additive identity n plus 0? Why was it that I knew 1/3 and 1 would get me that multiplicative identity of 1? And it's because of inverses. Inverses are going to take you back to your identity element. So if I start with some a plus b, and I want a and b to be inverses, what I really mean is that when I add them together, they're going to take me back to the additive identity element of 0. Well, what kinds of numbers does this work for? If you wanted an actual example, we could imagine, say, like we did on the previous page, 5 and what, when I add them together, make 0. You're just incredibly loudly screaming at home now, oh, well, that thing must be -5, right? Or if I wanted to start with a negative, -7 plus what would equal 0, and that thing must be 7. So in general, we can say that a number and its opposite, in this case meaning the additive inverse for opposite, are going to have opposite signs, right? So we can say n plus -n will equal 0. And n and -n, because they take me back to the additive identity element, remember that's what that is right there, additive identity element of 0, we would call these additive inverses. Does the same thing work under multiplication, you're wondering? Yes, it does. So let's say we wanted the multiplicative inverses, such that we have something like a times b. This time doesn't equal 0. We're not trying to get back to the additive identity element. We're trying to get back to the multiplicative identity element. So we're going to try and get back to 1. What kinds of numbers would that work for? Let's do an example. Again, on the previous page, we used 3, right? 3 times what would end up giving us back 1. It can't be a whole number like 3. 3 times 3 would be 9. That's much too large. It can't even be something as small as 1, the additive inverse, the multiplicative identity itself. 3 times 1 is 3. That's still too large. We obviously need a fraction here, some kind of fraction or decimal. And specifically, we need something that we call a reciprocal, right? 3 times 1/3 equals 1. Or if we wanted to start with something that looked like a reciprocal, 1/10 times 10 equals 1. Or we can just start with a generic old fraction, right? 2 over 7 times 7 over 2 equals 1. So again, in general, if we started with some number n, it would be its reciprocal, 1 over n, that gives us back the multiplicative identity element of 1. So we would call these multiplicative inverses. And of course, when we multiply them, they generate the multiplicative identity element. So there you have it. That's what an identity is, that's what an inverse is, and that's the connection between the two of them. I hope you have enjoyed your Wednesday Math Minute, the only Math Minute guaranteed to be Wednesday, and guaranteed to be, in this case, just under 8.5 minutes long. I bet I can cut 40 seconds.